We'll now continue in section 7.2, and we will discuss some applications of our sum and difference identities. Let's begin with an easier problem. This problem asks us to use a difference identity to verify that sine pi over 2 minus x is equal to cosine x. So we have practiced establishing identities in the last couple of sections. We know that we are told to start with the more difficult side and try to turn that side into the easier side. So I'm going to begin with sine pi over 2 minus x. Now, I want to recognize this as a version of my difference formula for sine. So I'm going to go back and take a look at that formula, keeping in mind that my first angle is pi over 2, and my second angle is being played with by an x. So here is my formula for the difference of two sine angles. Remember that the first angle is being played by pi over 2, and the second angle is being played by x. And so let's go ahead and look at what the other part of our formula is going to look like. We're going to have sine pi over 2 cosine x, cosine pi over 2 sine x. And so I'm going to take the right-hand side of this equation and go back to my problem and write that down. So again, we're going to have sine pi over 2 cosine x minus cosine pi over 2 sine x. Now, let's plug in what we know. We know that the sine value at pi over 2 is equal to 1. I do not have any way of simplifying cosine x, so I'm just going to bring that down. Cosine at pi over 2 we know is equal to 0. And again, sine x is just going to be brought down because we can't simplify that part at all. And so if we look at what we have, as we simplify further, we have 1 times cosine x, which is cosine x. And we have 0 times sine x, which is going to fall away. And so we have now shown that sine pi over 2 minus x is equal to cosine x. Okay, so let's move on to a second example. We're asked to express sine tangent inverse of x plus cosine inverse of x as an algebraic function of x. Recall that when you're doing an inverse function, that the answer to an inverse function is always an angle. So as I look at this expression, I'm going to go ahead and say that the answer to this, again, remember that the answer to an inverse function is an angle. I'm going to say that the answer to that is u. We'll call it angle u. Okay? And then we're going to do the same thing for the cosine. So we're going to say that the answer to this part, which again is an inverse function, so the answer should be an angle, we'll call it angle v. So if you look at what we have now, we have sine u plus v. And I can go back to my formulas and I can write a formula down for this. Sine u plus v is my top formula here. And so all I'm going to do to begin with is just transfer this formula to my example. So sine u cosine v plus cosine u sine v. Now, my next step is to plug in something for each of these four terms. I need to plug something in for sine u, for cosine v, for cosine u, and sine v. Now, because these are somewhat generic in terms of having a variable instead of an actual angle, it's going to be difficult for me to give an exact answer for that. So what I'm going to do instead is I'm going to draw a triangle. I'm going to draw a picture for each of these angles. Okay, so for angle U, I'm going to draw my right triangle. We're going to put angle U here, and we're going to plug in what we know. Okay, so we know that tangent inverse of x is equal to u. So remember that this means, if we switch it back to the regular trig function and not the inverse, this means that the tangent of angle u is equal to x. Now I'm going to treat that x as a fraction over 1. And in doing so, that gives me, remember your SOHCAHTOA, that gives me my opposite side and my adjacent side of my triangle. So I'm going to go back to my triangle, and the opposite side I'm going to call x, and the adjacent side I'm going to call 1. Now that allows me to go in and determine the hypotenuse of the triangle. So I'm going to use Pythagorean. I'm going to say my first leg, which is 1 squared, plus the second leg, which is x squared, is equal to, and for now let's call the hypotenuse c. And I want an expression for c, so I'm going to go ahead and take the square root of both sides of the expression that I have. And this tells me that 1 plus x squared underneath the square root is equal to c. And so I can now come back to my triangle, and I can say that side c is going to be 1 plus x squared. Now, you may be asking yourself, does that really help us? It does, because remember that we're trying to write an algebraic function of x. So now, if I'm being asked to find sine u, for example, I can use my triangle, and I can say that sine of this triangle is opposite over hypotenuse. And so I can go ahead and fill in sine u. So the opposite side will be x. The hypotenuse will be the square root of 1 plus x squared. Okay, I can also go ahead and fill in cosine u. So cosine, remember SOHCAHTOA, is your adjacent over your hypotenuse. So we'll have 1 over the square root of 1 plus x squared. Now, we need to do something similar for v, right? So I'm going to erase this, and we're going to go ahead and do the same approach for angle v. So I'm going to draw a right triangle. I'm going to label an angle v, and let's look at what we know. We know that cosine inverse of x is equal to v, which again, remember when we take that out of the inverse form, that means that cosine v is equal to x. I'm going to write the x over 1, and remember my SOHCAHTOA. So this is my adjacent side, and this is my hypotenuse. So I'm going to plug in as an adjacent side x and hypotenuse of 1. All right, so let's find the missing side. So we'll do Pythagorean again. So we'll say x squared plus, let's call this missing side b. B squared is equal to 1 squared. So I have x squared plus b squared is equal to 1. Remember that you're solving for b. So we're going to subtract the x squared from both sides. And then we'll take the square root. So this tells me that b is equal to the square root of 1 minus x squared. And so we'll plug that in for side b. And back to our problem, let's look at what we need from this triangle. We need cosine b. So again, cosine is going to be adjacent, which will be x, over the hypotenuse, which will be 1. We also need sine b. Sine will be the opposite over the hypotenuse. Now, let's look at what we can do to simplify. For our first set of fractions, x times x is going to be x squared. And for the denominator, we'll be multiplying the square root times 1. For our second set of fractions, on the top, we'll multiply 1 times the square root. So that's just going to leave me the square root. And on the bottom, we'll have the square root of 1 plus x squared times 1. And so it's perfectly acceptable to leave your answer in this format. This is an expression in terms of x. You also have the option, since the denominators are the same, of pushing these two fractions together, in which case you could write something along the lines of x squared plus your square root divided by the square root of 1 plus x squared. And either answer would be acceptable. Okay, so let's move on to our next example. Our next example asks us to use the sum and difference identities to show that sine of x plus h minus sine x over h is equal to sine x times cosine h minus 1 over h plus cosine times sine h over h. And this problem is one that, upon first glance, looks fairly difficult. So let's start with the left-hand side. Now, the only reason that I'm not starting with the right-hand side is that I don't instinctively see anything particular that I can do with the right-hand side. However, I noticed that on the left-hand side, we have a sum of a sine, and I know I have a formula for that. So I think that's where I'm going to start with this one. So I'm going to write my left-hand side down with the intention of trying to turn it into the right side. Okay, so the first thing I'm going to do, like I said, is I'm going to take this part and I'm going to apply my formula. So remember that the formula for the sine with the plus in between is going to be sine of the first angle times cosine of the second plus cosine of the first times sine of the second. So I'm going to apply that formula to what I have here. So we'll have sine x times cosine h plus cosine x times sine h. And then at the end, I have a minus sine x. And it's all divided by h. Now, what I notice as I'm looking at this is that the second part of the equal to, I kind of have that here. If I look at this term right here, cosine x sine h, that's the top part of this fraction here, cosine x sine h, and it can be over h. So I think what I'm going to do is kind of rearrange my terms a little bit. I'm going to leave this first term. That takes care of that one. I'm then going to go get the last term. So minus sine x And then I'm going to put this third one in last. And this is just addition and subtraction, so it's fine for me to rearrange terms. Now, the next thing I'm going to do is, since both of these are over h individually, I'm going to go ahead and break this fraction up. And so I'm going to separate right here, and I'm going to put this fraction over h and this fraction over h. And in doing so, this takes care of this last term. I'm going to have to separate it out, which I'll do in the next step, but otherwise that is finished. Okay, so let's look at this one. This one is supposed to have a sign pulled to the front. So let me go ahead and do that and see where that leaves me. So if I take a sign out, my first term is going to be left with a cosine h. And taking a sign out of this negative sine x is going to leave me a negative 1. And I still have the h in the denominator. All right, and then I'm just going to rewrite this term, pulling the cosine to the front. And it appears with that I have done what I set out to do. Okay, so we're going to look at one more example in this presentation, and this example pulls from a theorem. All right, and so it comes from this theorem. Now, I know that this is a lot to look at as we glance at it, and we're going to come back and kind of play with it in just a minute when we look at the example, but this is what we're going to be using in order to work the problem that we have. Okay, so our problem says express the function f of x is equal to sine x minus the square root of 3 cosine x in terms of a single sine function, and then graph the result. Okay, so the first thing I'm going to do is I'm going to go back to this problem here, and I'm going to write my problem at the top so I can do some comparing. All right, so my problem said f of x is equal to sine x minus the square root of 3 cosine x. Okay, so that is the problem in my example that I'm trying to work with. So as I do that, what I notice is that the a value is the number that sits in front of the sign, which for us is a 1. And the b value is the number that sits in front of the cosine. For us will be negative square root of 3. So I know right now that a is 1 and b is negative square root of 3. Okay, so what that allows me to do now is to go ahead and do some of these initial calculations. One thing that I notice in my problem quite a bit is this expression right here. So I'm going to go ahead and calculate that based on my a and b values. All right, so I would then have a squared, which would be for me 1 squared, and then b squared would be negative square root of 3 squared. So 1 squared is 1. Remember that when you square a square root, first of all, it's going to become positive because we're squaring that negative. And then when we square that square root, it's going to come off, leaving me just 3. So we have the square root of 4, and so we have 2. So this part of my expression is going to equal 2. And you can see that that is in a lot of places in the formula. Okay, it's going to be here, it's going to be here, and also here. Now, we also know that cosine of angle omega is equal to a over the square root of a squared plus b squared. So we can go ahead and calculate that fairly easily, and I want to do that with you next. All right, so cosine of that omega is equal to the a value, which is going to be 1, over this square root that we found to be 2. So we know that cosine of the angle is 1/2. We also know that sine of the same angle will equal the b value, which is negative square root of 3. And again, that square root we calculated to be 2. So if we keep that in mind and think about our values, we can go ahead and deduce that that angle would have to be negative pi over 3. Okay, so let's think about how we know that. Okay, so I'm going to come over here and just kind of jot this down, what we know. We know that cosine of the angle is 1/2. And we know that sine of the angle is negative square root of 3 over 2. Okay. Okay, so think about your signs in the quadrants. All right, so we know that cosine is positive. It's positive 1/2. So that tells me that my angle is either in the first quadrant or the fourth quadrant. Okay, for the sine, we know that it's positive in the first and second, negative in the third and fourth, and our sine value is negative. So we're either in the third or the fourth. So we know that our angle lies in quadrant 4. Okay, so once that's decided, then we need to figure out what the angle actually is. And so we know that cosine is equal to 1/2 at pi over 3. And sine is equal to square root of 3 over 2. I'm ignoring the negative for just a second. Also at pi over 3. So we know that both of these have to do with a pi over 3 type angle. Now we do need that to go to the fourth quadrant. So let's go ahead and think about what that angle is going to look like if we rotate down into the fourth quadrant. So we're going to rotate down pi over 3. And so that angle will be negative pi over 3. You could also say the angle was 5 pi over 3 if you're moving in a positive direction. All right, so let's sort of summarize what we know and let's finish this problem up. All right, so I know that my angle is equal to negative pi over 3. I know that my square root of a squared plus b squared, we found that to be 2. We know that the a is 1. We know that the b is negative square root of 3. Okay, so let's go back to our formula, and we're almost done here. Let's take this part, this is our equal to part, and let's plug in for our answer. All right, so that is the square root of a squared plus b squared sine x plus omega. All right, and we're going to plug in what we know. We know this square root's equal to 2. And we know that our angle is negative pi over 3. And so this will be our answer. This is a single sine function. And we have expressed the original function in terms of that single sine function. Now, the problem also asked me to graph, which, remember, we're going to use our graphing techniques in order to do that. All right, so we know that the amplitude on the graph is going to increase to 2 because we have a 2 right here. We also know that we're going to have a phase shift because we have that negative pi over 3. And so that final graph is going to look something like this.